Hey everyone, welcome back to another video by Camroom 5. In today's video, we are going to be talking about halogens, including fluorine, chlorine, bromine, iodine, and astatine. Astatine is not much of a concern here. We'll be talking about the first four halogens. So when we talk about the first four halogens, fluorine is a pale yellow gas. Fluorine is extremely reactive, by the way. Chlorine is a pale green gas. Bromine is an orange brown liquid at room temperature pressure, while iodine is a gray black solid with violet fumes. So, fluorine is a pale yellow gas, chlorine is a pale green gas, bromine is an orange brown liquid, iodine is a gray black solid with violet vapors. When we talk about their molecular arrangement, you can see the fluorine atoms are diatomic. The molecule is diatomic in nature. The atoms are really strong. Chlorine atoms are bigger, but the molecule is still diatomic. Bromine, being a liquid, should be having a kind of clustered arrangement of particles, unlike chlorine, which has the gaseous nature. So bromine particles are clustered in the liquid state, where the particles are in layers and obviously in clusters. You can see these particles are sliding past each other, but you can't call it translatory motion. And also notice one thing, that bromine atoms are much bigger than chlorine or fluorine atoms. Iodine is a solid which has the biggest atoms. The explanation involves that they have ID forces between particles, and that is why the state of matter changes. They have ID forces, London dispersion forces, between these molecules. Fluorine molecule is smaller, so it has less electrons than obviously bromine or iodine. So it has less electrons compared to a Br2 molecule or even I2 molecule. That is why fluorine particles do not have very strong ID forces. So as a result, bromine and iodine have higher ID forces. Fluorine and chlorine have less ID forces, because more electrons in a molecule results in stronger ID forces. And that is why their boiling point increases. Now we are going to be talking about hydrogen halides. By hydrogen halide, we mean hydrogen in a bond with a halogen atom. It's a binary compound. A binary compound means a compound with two distinct elements. It's a binary compound of hydrogen with a halogen. Like HF is hydrogen fluoride, then HCl, then HBr, and then HI. You can see I am drawing them with longer lines. I'm trying to make a point here. You will see later. So we have hydrogen fluoride, hydrogen chloride, then hydrogen bromide, which is HBr, and hydrogen iodide is HI. When we talk about their boiling point values, I am drawing a graph here which has negative and positive both temperatures. Hydrogen fluoride has a higher boiling point, which is around 20-ish. But HCl has a very low boiling point, which is in the range of minus 84-ish. Then HBr and HI have higher boiling points than HCl. First, talk about description of what we see. A description does not involve reasoning. A description means what you see. So the boiling point decreases from hydrogen fluoride to hydrogen chloride. But then it continuously increases. Then continues to increase from HCl through HBr and HI. So HI has higher boiling points than the previous two. Now we'll talk about the explanation here using the intermolecular forces. Hydrogen fluoride particles have hydrogen bonding in them. You can see I'm drawing some hydrogen fluoride molecules here. They are highly polar, and fluorine has lone pairs. So you will mention dipole on the hydrogen fluoride molecule, which means fluorine is partially negative and hydrogen is partially positive, and you will draw hydrogen bonds from the lone pair of the fluorine atom to the partial positive hydrogen atom. These are very strong hydrogen bonds. That is why HF has a higher boiling point. Now we'll talk about HCl, HBr and HI. HCl has hydrogen and chlorine atom in single molecule. The Cl atoms are not very big compared to bromine and iodine. The overall HCl molecule has few electrons, most of which are because of chlorine. Hydrogen has single electron. And because of the electrons, because of the overall electrons in the HCl molecule, there is ID forces here. So ID forces are made between HCl molecules which are not very strong. As a result, HCl has very low boiling point. When we talk about HBr or HI, the H atom is common. But what is important? The HBr molecules, as you can see, have bromine atoms which have more electrons and more shells. So there are total electrons which are more than HCl molecule. Because of more total electrons, you will have stronger ID forces. Stronger or more ID forces. When we talk about HI has even bigger atom, which is iodine. Iodine is in the 5th period. It has 5 electronic shells. So there are more electrons around iodine than even bromine. The electron cloud is really big, so you can say more total electrons. As a result, more ID forces, more total electrons, and as a result, more ID forces. So more total electrons in HI compared to HBr or HCl. So as a result, finally more ID forces. And that is how we explain the boiling point increment from HCl to HBr to HI. Now we'll talk about the reactivity of the hydrogen halides. When hydrogen reacts with fluorine, we get hydrogen fluoride. It's a pretty explosive reaction where it becomes very quick reaction even in dark conditions and even in cold environment. It's pretty explosive under sunlight. Let's not talk about what happens when we heat the process. When we talk about hydrogen reacting with chlorine, it's still a very vigorous reaction and we get hydrogen chloride. Hydrogen chloride and hydrogen fluoride are very good strong acids. Hydrogen chloride is better acid than hydrogen fluoride. It's a violent reaction in sunlight and a little less quicker than hydrogen fluorides. When hydrogen reacts with bromine, we get hydrogen bromide. HBr is produced here. It happens at a fair speed when heated. So reacts like slowly on heating, so it's not like very quick reaction. Just notice the trend that reaction is becoming less vigorous. Hydrogen and iodine make hydrogen iodide. It never reaches completion. Even if you heat it, it will never become a complete reaction because that is reversible. The reason can be explained by their atomic and molecular structures. I have drawn all the hydrogen halides here. Do you see the difference? The bond lengths are different. HF has very short bond, the bond length is very short. So the bond energy is really high, it means it's a very strong bond. So it will release a lot of heat energy when the reaction happens, and that is why it's explosive. It's the strongest bond here and it will release a lot of heat energy, so it's very exothermic. Energy is released here, the enthalpy is really negative. But when you compare HBr and HI, HI has a very long bond length. And since the bond length is more, you can expect that the bond energy would be lower, lowest bond energy. It's not a very strong bond. And as a result, it's a very weak bond. It won't release energy. And that is why, even on heating, it does not reach completion because it's not very exothermic or feasible reaction. So it will release very low energy. And that is all because of the bond lengths. HI will immediately absorb heat energy, the bond will break down and will make H2 and I2. That's called decomposition because it's easier to break the HI bond. But HF is very stable because of the short bond and stronger energy. So in today's video we have talked about all the hydrogen halides and halogens. In next video we'll talk about redox of halogens. Stay tuned guys.